Hello, in this video we're going to talk about two things. First is an explicit formula for the inverse of a matrix, and second is what we call the Cramer's rule. So here is the first theorem. Let A be an invertible matrix, then ij, the ij entry of A inverse equals -1 to the power of I plus j, determinant of A ji. Notice that I and j are swapped, so you remove the jth row and ith column of A, you get A sub ji divided by the determinant of A. Okay, so we are going to prove this theorem. Let's for simplicity call that Bij. Let Bij be -1 to the power of I plus j, determinant of A ji divided by determinant of A. Now I'm going to take a matrix consisting of Bij's, and then I'm going to multiply that by A, and then I show that that is the identity matrix. So let B be Bij, and this is an n by n matrix. So the n by n matrix whose ij entry is Bij. Now we're going to multiply A and B and show that that is in fact the identity. So the ij entry of AB is the sum AIL BLJ, and this L goes from 1 to N. And here AIL is the IL entry of A. So let's evaluate that and see what we get. So the sum AIL, L equals 1 to N, BLJ. So BLJ, if we look at this, we'll have to replace I by L. So we get -1 to the power of L plus J, determinant of A, JL, divided by determinant of A. We will have to show this is in fact 1 when I and j are the same, and 0 when I and j are not the same. So if you think about this one, L is changing, so AILs are just the ith row of A, and this one is, again, J is fixed but L is changing. This is a matrix obtained by removing the jth row, J is fixed, and lth column of A. So what does that mean? It means if you take A and replace the jth row by AI1, AI2, all the way to AIN, and the rest of this is A. So this is the determinant of the matrix obtained by replacing the jth row of A by the ith row of A. So how do we know that? Because if you do a row expansion, cofactor expansion along the jth row, you would get AI1 determinant of removing the jth row of A and removing the first column of A. And that's exactly this. And then AI2 removing the jth row of A and removing the second column of A. And again, we get the same thing. So now we got a matrix that the jth row of that matrix is the same as the ith row of A. If I and j are the same, this is exactly the matrix A. This is just, and there's a 1 over determinant of A that I forgot. So it's 1 over determinant of A. So if I and j are the same, that's just exactly the determinant of A. So it's determinant of A over determinant of A. And if I and j are not the same, then this matrix is going to have two rows that are the same. The ith row and the jth row are the same. So this is 0. So if I and j are not the same, we're just going to get 0. So what does that mean? That means when I multiply A and B, I get 1 on the main diagonal and 0 everywhere else, which means that is the identity matrix. Now, if you look at a matrix, if you have A, B equals identity, then you can also show that B, A must be identity. That's not very difficult, and the reason is this. First of all, if you take the determinant of both sides, you will get that determinant of A times determinant of B is 1, because the determinant of identity is 1, and that tells you that determinant of A isn't 0, which means A is invertible. So if A is invertible, then we can multiply by the inverse of A. So we can do A inverse AB equals A inverse identity, which is A inverse, and that tells us B is in fact A inverse. So in other words, the matrix that we found, Bij, is in fact the ij entry of the inverse of A. And that's exactly what we wanted to prove. So we proved that inverse of a matrix can be found using this formula. The ij entry is -1 to the power of I plus j, determinant of A, ji. Okay, so let's do an example on this one. Let's say you have a matrix A, a 2 by 2 matrix, A, B, C, D, and we want to find the inverse of this one. So inverse is going to be 1 over determinant, which is AD minus BC. Now, what I need to do is I need to do -1 to the power of I plus j, 1 plus 1. Then I will have to remove, this is 1, 1 entry. I'll have to remove the first row and the first column and then take the determinant. So removing the first row and the first column, take the determinant, you will get D. This one is -1 to the power of 1 plus 2, because this is the first row, second column. Now I'll have to remove the second row and the first column, and I will get B. -1 to the power of 1 plus 2. Then I'll have to remove, this is second row, I'll have to remove the second column and first row. So that would be C. And finally, -1 to the power of 2 plus 2, A. So this would be 1 over AD minus BC, D, A, -B, -C. And this might be something that you have seen before, and if not, then this is basically the inverse of a 2 by 2 matrix. It's not very difficult to see that if you multiply A, B, C, D by that, you get in fact the identity matrix. Okay, so let's move on to the next theorem. This is a very important theorem. It allows us to find solutions to a system. So first, what does it say? And then we're going to prove this. Let A be an invertible matrix, then for every column vector B, the only solution to AX equals B is that, and xj is given by the determinant of A1 through AJ minus 1, B, and then AJ plus 1 all the way to AN. What does that mean? It means you take the jth column of A, you replace it with B, which is the other side of the equality, take the determinant, and then divide by determinant of A. So AX equals B, I know that A is invertible. That is the same as X equals A inverse B, because we could just multiply both sides by A inverse and we get to X equals A inverse B, and we could also go backwards. So these are the same thing. Now let's just use the formula that we had for A inverse. So xi, the ith entry would be, so xi would be the sum A inverse. I'll have to take the IL entry and then multiply by BI. BL. L equals 1 to N. So let me tell you what these are. B is just B1 through Bn. A inverse IL is the IL entry of A inverse, which we know what it is. This is -1 to the power of I plus L determinant of, it's the IL entry, so it would be Li here. If you recall, you have to swap that, divided by determinant of A. If we take that and plug it in there, we get xi equals the sum L equals 1 to N, this quantity, negative 1 to the power of I plus L, determinant of A Li divided by determinant of A, and then I'll have to multiply that by BLI. I'll put the BL right here. If you think about this one, this is basically a cofactor expansion along the ith column. So look at this matrix. This matrix is take the ith column and remove the ith column and the lth row. I is fixed, so we keep removing the ith column. And we multiply that by BL. So we do B1 all the way to Bn here. And the rest of the matrix is going to remain the same. So it would be A1, AI minus 1, AI plus 1, all the way to AN. And then divided by determinant of A. That doesn't change. So this is how we can find all the solutions. And that's exactly what we had in the Cramer's rule. Now, let's do an example for Cramer's rule. Solve the system of equations using Cramer's rule. So we have a system of equations. Let's write down the matrix A. The matrix A, the coefficient matrix would be 1, 1, negative 2, 0, 1, 2, 1, 0, and negative 1. And the constant on the other side is 1, 1, 3. So we will get x equals, we have a determinant of A at the bottom. On top, I will have to take the coefficient matrix, replace the first column by B. So it would be 1, 1, 3, 1, 1, 0, negative 2, 2, negative 1. Y would be, you have a determinant of A at the bottom again. On top, we take the second column, this is the column corresponding to Y, and replace it with B. So 1, 1, 3, and we keep the last column. And finally, Z would be, you have a determinant of A at the bottom, and we replace the third column, which is the column corresponding to Z, by B. 1, 1, 0, and then 1, 1, 3. And after evaluating these, we can get X, Y, and Z. And that brings me to the end of this video. So I will see you in the next video.